Okay, continuing on with Chapter 13. This starts with Section 13.5, Colligative Properties, and we'll also in this lecture continue on through Section 13.6. It is just 2 sections in the Burge chemistry book, but there's a lot to cover here. Colligative properties, defined as the properties that depend on the number of solute particles in solution, regardless of the nature of those particles. So whether it's molecules or ions or atoms, that's what that means. The nature doesn't matter. It depends on the number. And we'll kind of tie that definition in more when we reach the end of our lecture on colligative properties. There are 4 colligative properties we're going to discuss. They are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. And so as we take these individually, each of these has a formula that goes along with it. So first, let's talk about vapor pressure lowering. And the formula for vapor pressure lowering, it obeys a law following Rolle's law. The formula is P1 is equal to X1 times P1 with the little degree symbol, if you will. Okay, so what is vapor pressure? If you have, we've talked about it in Chapter 11, I believe, but if you have a closed container, okay, this has a lid on it, and you have a solvent, a liquid solvent in this container, and it can be water, it can be anything, but it's a liquid, then you know that in the air above this liquid, particles of that liquid have vaporized, and they exert a vapor pressure. And we talked about it in Chapter 11, like around your home, maybe it's a gas can in your shop, for your lawnmower or whatever. Y'all know that there's gasoline in the can, but that, especially in the summertime, as it heats up, that gasoline will vaporize, and sometimes those plastic cans they swell, right, because it's a really high vapor pressure. So yeah, the vapor pressure of the pure solvent is linked to the temperature. But the idea, well, P1 standard is the vapor pressure of the pure solvent. Okay? And the idea of vapor pressure lowering is that if we dissolve some particles, solute particles, okay, it's a colligative property, if we dissolve some kind of particles in this solvent, that the vapor pressure that we see above the solution will actually lower. So less of the solvent can vaporize. How many particles you have dissolved determines how much the vapor pressure lowers. So the more stuff dissolved, the lower it gets. X1 in this formula stands for the mole fraction of the solvent in solution. And then just the regular old P1 is the partial pressure of the solvent over the solution. And so as we're discussing this, the partial pressure of the solvent is going to be lower than the vapor pressure of the pure solvent. And it's partial pressure because when you dissolve something in the solution, you've got more than one species contributing to the vapor pressure. And so when we're, if we have like in air, guys, you got, nitrogen, oxygen, and other gases. Well, you would say the partial pressure of nitrogen in air is, like 0.8 atmospheres, if you will. Okay, so it's Notice that in this formula, to try to explain everything, the little ones on the bottom are designating that it's all about the solvent. Okay, that's what the ones are. Just remember, the ones are referring to the solvent. Mole fraction is kind of a new thing. We haven't talked about a mole fraction. But to calculate the mole fraction, it's the mole fraction of the solvent in the solution. So to calculate that, what you will do is take the moles of just the solvent, because it's the mole fraction of the solvent in the solution, and you're going to divide that by the total moles of the whole solution. Okay, so remember, solute plus solvent equals the solution. So to get the mole fraction, you take the moles of the solvent and divide it by the moles of the solute plus the solvent. Okay, that would be the total moles of the solution. It's kind of like a percent because it's the solvent divided by the whole thing, right? It's the part over the whole. But look, when you're doing a mole fraction, you're not going to multiply it by 100%. Mole fractions are going to be decimal answers, okay? They're not percentages. The P1, again, will always be lower than the P1 little degree symbol, than the pure stuff, because X1 should always be a decimal. So mathematically, it always has to work this way. So let's excuse me. Let's practice a calculation. And I'm just going to work the sample problem 13.5 in your book. It's worked for you, but we're gonna unroll it here. Let's calculate. Got a little lag there and got sloppy with my writing. The vapor pressure of water over a solution when 225 grams of glucose is dissolved in 575 grams of water at 35 degrees Celsius. And we want to know that at this temperature, the standard pressure of water is 42.2 millimeters of mercury. Okay. Do you remember the formula for glucose? I mean, that's one you've been exposed to quite a bit through biology and chemistry. What's the formula for glucose? Okay, it's C6H12O6. So if we're calculating the vapor pressure of water over a solution, obviously the P1, that's what we're calculating. The P1 with the little degree symbol is given as 42.2 millimeters of mercury, and we can leave it in those units. It's not necessary that it's converted to atmospheres, so we'll just work with millimeters of mercury as the pressure. And so X1 is going to be the mole fraction. Okay, but it's the mole fraction of the solvent, moles of solvent. What is the solvent in this problem? What does that say that I just underlined? Glucose is dissolved in water. So the solvent is the water. See, it's very common on these problems because you're used to doing like molarity and molality, that you take the solute, because in molarity and molality it's solute over, solvent, or solute over solution. But in a mole fraction, it's the solvent over the solution. So you take the moles of water and divide it by the moles of the water plus the moles of the glucose. So we've got to convert grams to moles, right? 575 grams of water to moles. And for moles of water, just dividing by the molar mass, I get 31.91 moles of water. And so for the bottom, I've got 31.91 moles of water plus my moles of glucose. So the molar mass of glucose, let's see. I got 180.18 for the molar mass of glucose. Molar mass is 180.18. So the moles of that. I've got 1.249 moles of glucose. So, for my mole fraction, I have 0.962. And mole fraction is a unitless number, okay, because it's moles divided by moles, so it doesn't have any units. And so now I can do that the P1 is equal to 40, well, let's do it in the right order. 0.962 times 42.2 millimeters of mercury, and I'll tell you, when I'm entering this in my calculator, like even though I'm writing here 0.962, I haven't cleared my calculator out. So my number that I'm actually multiplying here is the whole thing, the 0.962333300, etc., etc. Okay, so I'm taking the whole thing in. I got 40.6 millimeters of mercury. And so I'm thinking about this number as I calculate, right? I said that it's vapor pressure lowering. So the vapor pressure of the solvent when it's in a solution, which is this number, should be lower than the vapor pressure of the pure solvent, and it is. So I'm thinking as I do this and making sure that my numbers follow what the colligative property says that it should be. Okay? The next two colligative properties, we're going to kind of take those together because the next two that we listed are freezing point depression and boiling point elevation. And so, freezing point formula. So it's freezing point depression, okay, so lowering, boiling point elevation, so increasing. Those formulas look like this, that the delta TF is equal to KF times M, or delta TB is equal to KB times M. So, y'all know what the little triangle means, delta. It means change in. So the delta T, obviously the F's are for freezing and the B's are for boiling. So the delta T, what you're actually calculating is the change in the temperature, okay? Note, you're not calculating the temperature. You are calculating how much it changes by. So it's different from what we just did. We calculated the vapor pressure. If we wanted to know how much the vapor pressure changed by, we would subtract these two numbers. That's the difference. But in the freezing point and boiling point calculations, you're calculating the change. Okay, I can't stress that enough because it's a common mistake on these calculations. All right, the KF and KB, those are constants. KF / KB stands for Malal freezing point constant. Or, of course, if it's KB, it's the Malal boiling point constant. Okay? And those are not like ideal gas constant. If I asked y'all what the ideal gas constant is, I think you could all tell me because you've used it enough. y'all all know that the ideal gas constant that we use is 0.0821 liters times atmospheres per mole times Kelvin. Okay, freezing point constants are different depending on the solvent. So we don't memorize those. They don't, there's a lot of different ones, okay? So you're going to want to look at table 13.2 in your book. And in the, what are we in, the 5th edition? In the 5th edition, that's on page 579. So you don't memorize these, but you realize that those numbers are available to you on the table. Okay, and then finally in this formula we have the M, which looks familiar, right? It's the molality. And we all remember that the molality is the moles of the solute divided by the kilograms of the solvent. Okay? So, to practice this one, again, we'll just do the sample problem 13.6 in your book. Which uses ethylene glycol, which is antifreeze. Well, I can't spell. Is dissolved, I'm kind of rewording it, in 2,075 grams of water. So let's say, we'll use the numbers they have. 685 grams of ethylene glycol is dissolved in 2,075 grams of water. Okay, let's calculate. It asks us to calculate both the freezing point and the boiling point. And we're also given the formula for ethylene glycol, because that's not one that, of course, I'd expect you to know. It's an organic one. Okay, that's formula for ethylene glycol. So first, let's calculate the freezing point. Okay. Delta TF is equal to KF times M. The KF is going to be a constant. The Malal boiling point constant we would get, Malal freezing point constant, we would get from table 13.2 in our book. And if you look up the KF, it lists different solvents, okay? What is the solvent in this? It's in the context of the reading, right? The reading says it's ethylene glycol in water. That tells us that the water is the solvent. You've got to be able to identify from the context what the solvent is. So the KF for water is 1.86 degrees Celsius per molal. I got that from the table. The molality is going to be, how do I calculate the molality? Well, we know that molality is moles over kilograms. But in reference to this problem, moles of what? It should be moles of the solute. So it's the moles of the ethylene glycol over the kilograms of the solvent, which is the water. So quickly, I've got the kilograms of the water, right? Kilograms of water is 2.075 kilograms of water. And now I have to calculate the molar mass of ethylene glycol and convert grams to moles. And here's where I really wish we were sitting in class, because sometimes I mess up on the calculation and you guys will catch that for me. I'm doing the molar mass of ethylene glycol. I got a molar mass mass of 62.08. I am going to double check that because I hate when I work the whole thing and realize, yeah, 62.08. Realize I did the wrong thing. Okay, so that's the molar mass. So 685 divided by that number is my moles of ethylene glycol. .03 moles. Grams divided by the molar mass. So my molality is 5.318 molal. Okay, so now I'm ready to calculate the delta T by plugging things in. So the delta T is equal to the Kf, 1.86 degrees C per molal, times the molality, which is 5.318 molal, so the delta T F is 9.89 degrees Celsius. Okay. Did we calculate the freezing point? We calculated the change in the freezing point. Okay, so we have not answered the question when it says calculate the freezing point. We haven't done that yet. All we've done is calculate how much it changed by. Okay, now this is water. You guys know, what temperature does water freeze? That one you know. It normally freezes at 0 degrees Celsius. Okay, so the normal freezing point of water is 0 degrees Celsius. This colligative property is freezing point depression. So we have lowered the temperature by 9.89 degrees Celsius. So the answer to this question, what is the freezing point, is negative 9.89. Okay, now I don't mean to insult your intelligence, but the answer to the freezing point is not always just the negative of the change, right? It just works out this way because water's freezing point is 0 degrees Celsius. If you had been putting this ethylene glycol in benzene, well, benzene's freezing point is 5.5. So you would have had to say 5.5 minus 9.89. Okay? So, Ms. Hurt, how do I know benzene freezes at 5.5? Well, you find those freezing points of those other solvents on table 13.2. Okay? So water you would know, but if it was something like benzene or what else is listed on that table? Ethanol, acetic acid, cyclohexane, you would be given that. Okay? Now, let's use the other half of this screen then to calculate the boiling point of this. Okay, delta TB is equal to KB times M. And we've already done most of the work because we've already calculated the molality. The KB, I'm going to get that from the table. The KB for water is 0.52 degrees Celsius per molal. And the molality is still 5.318. So the change in the boiling point is 2.77 degrees Celsius. So what is the boiling point? What's the normal boiling point of water? The normal boiling point of water is 100 degrees Celsius. The colligative property of boiling point is boiling point elevation. So we have increased the boiling point by 2.77. So the new boiling point is 102.77 degrees Celsius. So for boiling point, it's elevation. So we're always adding it to the boiling point. And for freezing point, it's depression. So we're always subtracting it. Okay? And this is, ethylene glycol, as this problem states, I mean, it's antifreeze. It goes in your car's radiator. And you put water in your radiator because it helps cool the engine. But in the wintertime, you don't want your radiator, the water in the radiator, to freeze. And that's not a major problem here in Mississippi, but in some parts of the world, it gets very cold. And so you have to have enough antifreeze in your radiator so that the water won't freeze and then it busts and it cracks the radiator. Okay, that's going to be huge problems. Likewise, I mean, even here, when you're the water in the radiator is going to get hot because it's cooling the engine. And so water boils at 100 degrees Celsius. The more ethylene glycol that we have in there, we can cause that water, it has to get hotter to boil, okay? The more ethylene glycol you have, the hotter it has to get to boil. This is also, this freezing point depression, if you've ever made homemade ice cream. You know, you have your ice cream mixture and you fill the ice cream maker with ice all around and you put salt on that ice, right? So ice is 0 degrees Celsius. And yes, it's going to start to melt because you're doing this in your house, right? It's melting ice, but you put salt on it because salt is going to lower the freezing point. So that ice is going to get colder. And that's just a delicious way to use freezing point depression. Okay? The final colligative property that we want to talk about is osmotic pressure. And osmotic pressure is the pressure required to stop osmosis. Okay? We've heard about osmosis. What is osmosis? Okay, it's the movement of solvent across a semi-permeable membrane from dilute concentration to a higher concentration. Okay, so for example, I've got another video on my channel that talks a little bit more about osmosis, but if this is a U-shaped tube. Okay, right here, that is a semi-permeable membrane. And on this side, we're going to put just pure water. Okay, that's our solvent. On this side, we'll just put sugar water, right? So water's the solvent, but the sugar is the solute. So what's going to happen is this system recognizes, hey, I've got a different concentration on either side of the membrane. So the water is going to flow across the membrane in this direction. It goes from a dilute concentration to a higher concentration. And I mean, the way I think of it is the concentrations are trying to equal out. Okay? Now, in this, because I've got pure solvent on one side, they're not going to equal out. It can't dilute the sugar water enough so that the concentrations are going to equal, but it's going to try to. So what's going to happen is the water is going to flow that direction. That's going to cause the level over here to rise and the level on this side to drop. At some point, the water is not going to be able to pass that membrane anymore. And the difference in these two heights, that is the osmotic pressure, okay? It's the pressure required to stop osmosis. So the water can't flow anymore because that difference in pressure is too great. The formula for osmotic pressure that is the symbol for pi. osmotic pressure is equal to MRT, where the little pi symbol, it's not 3.14, it stands for osmotic pressure. Okay, that can be like atmospheres or millimeters of mercury or whatever. M, notice it's a capital print M, that's the molarity. R is the ideal gas constant, the same one, 0.0821, that we've been using. And T is the temperature. And since the R we're using has units of Kelvin in it, the temperature also has to have units of Kelvin. Of course, molarity is moles per liter, but you can see all those units in the value of the ideal gas constant. Okay, so let's practice more complicated osmotic pressure problem than some of the ones we've done. And I'm actually pulling this problem from the back of the book. It's just one that doesn't have the answer for you from the end of the chapter. A 0.86% by mass of sodium chloride. This is known as physiological saline. Okay, it's physiological saline because the osmotic pressure of a 0.86% sodium chloride is equal to the osmotic pressure of blood cells. When they're equal, when the osmotic pressure of the solutions are both equal, that's called isotonic. Y'all might have heard that in biology. The prefix iso means same, right? Like isotope or isosceles means the same. Isotonic, same osmotic pressure. It's physiological saline. Okay. Let's calculate, and I'm going to abbreviate it just because I don't want to write it out. I want to say calculate the osmotic pressure, but I'm just going to write the symbol here. Of this solution at body temperature. Do y'all know what body temperature is? Yeah, you know it's 98.6 degrees Fahrenheit. What is that on the Celsius scale? Body temperature. That's something once you've been through like microbiology, and you should know that. 37 degrees Celsius. Okay. To help us do this, we're going to need to know that the density of this saline is 1.005 grams per milliliter at this temperature. Okay. So I encourage you to pause this and see where you can get with this problem. Okay. Organize your information and think on it yourself. Okay, and then once you restart, obviously we're doing a osmotic pressure. And if we organize the information, we know this is what we're solving for. The molarity is going to be the moles of the sodium chloride divided by the liters of the solution. And the R is 0.0821. And the temperature is going to need to be 310 Kelvin. Okay, so the challenge here is really getting from the percent to the molarity. So let's break down that percent, 0.86. What that means is, it says it's by mass, so it means there's 0.86 grams of sodium chloride per 100 grams of the solution. So I need to convert grams to moles, and I'll have that answer. And then if I have the mass and I need the volume, the density will get me there, right? So 0.86 grams. I'm going to convert that to moles. Molar mass of sodium chloride is 58.44. So I'm going to divide this by 58.44 because that's how many grams are in a mole. And that's going to give me 0.0147 moles of sodium chloride. And then based on my density, okay, if density is mass over volume, then the volume is going to be equal to the mass divided by the density, right? So I'm going to take the 100 grams of the solution divided by the density of the solution. That's going to give me 99.5 milliliters, which needs to be liters. Okay, so I'm going to take these two numbers, plug them into molarity. For the molarity, I get 0.148 molar. And now I'm ready to go to the osmotic pressure formula. Okay, osmotic pressure is equal to M times R times T Okay, so for an osmotic pressure, I get 3.76 atmospheres. Okay, but I'm not finished yet because there's something new I need to introduce to you guys. Okay, we've got the right work so far on this osmotic pressure problem, but there's a concept we need to introduce because we're not finished with this one. Well, I need to introduce it to you. That is called the Van't Hoff factor. Okay? So if you look back, and I'm going to jump slides way back to the beginning, when we introduced colligative properties, defined it as the properties that depend on the number of solute particles in solution, but not on the nature. Okay, now think back to Chem 1. Ionic compounds. Sodium chloride is an ionic compound. How do ionic compounds dissolve in water? Do you remember talking about electrolytes and saying that they ionize? Okay, so what that means is, if you'll remember writing net ionic equations, that when sodium chloride dissolves in water, it dissolves as sodium ions and chloride ions. So even though we're taking a mole of sodium chloride and putting it in water, look, we end up with a mole of sodium and a mole of chloride. We end up with a total of 2 moles, because a 1 on the sodium and a 1 on the chloride, the total is 2. We end up with 2 moles of solute particles in solution. So that tells us that for sodium chloride, it has a Van't Hoff factor of 2. Van't Hoff factor is shown in the formulas, like Van't Hoff factor is given the symbol I. That's how it's often represented. And in the formula, when you do delta TF is equal to KF times M, or delta TB is equal to KB times M, or osmotic pressure is equal to MRT, there's actually an I here in the formulas. So that means for the one we just worked, since it's sodium chloride, the Van't Hoff is 2. That means there's a 2 in front of all this, which means we have to double the osmotic pressure. So the real answer is 7.52 atmospheres. Had this solution been talking about, say the molarity had worked out the same and it had been 0.148 molar, like sugar, okay? Sugar is a molecular compound. Molecular compounds are not electrolytes. They do not ionize in solution. So if you had like table sugar, C12, H22, O11, yes, it'll dissolve in water, but it stays as a molecule in water. So a mole of sugar is a mole of water in solution. So sugar has a Van't Hoff of 1. So there's still an I in the formula, but it's 1. And if you look back at the freezing point problem we did, it was ethylene glycol. Ethylene glycol here is a molecular compound, so its Van't Hoff is 1. So the answer we have is the answer because it only had a Van't Hoff of 1. Had this been sodium chloride, then the real answer would have been double the 9.89. Right? The change would have been twice that. So the freezing temperature would have decreased by double that amount. Now, is the Van't Hoff factor always double? No. Look at, for example, calcium chloride. How does calcium chloride dissolve in solution? It's an ionic compound, so it is an electrolyte. That means calcium chloride will dissolve as calcium ions and chloride ions, but aren't there 2 chlorides in calcium chloride? Yes, there are, CaCl2. So, what's the total moles that we have in solution? If we have 1 calcium and 2 chlorides, the total moles is 3. And colligative properties depend on the number of particles in solution. So calcium chloride would have a Van't Hoff of 3. So in the wintertime, when there's a threat of bad weather where the roads might ice, and what happens is the county or the city or whatever, they'll put salt on the roads. Y'all, what they salt the roads with is actually calcium chloride. Okay, now there's a lot of science going on there, and as to why that, like after there's ice, why it makes it melt, etc. But do you see that the reason they would use calcium chloride versus sodium chloride, one of those is because it has a greater Van't Hoff factor. Because calcium chloride would lower the freezing point 3 times versus sodium chloride only 2 times. Okay, and so there's multiple reasons for why it's calcium chloride, but that is one of them that pertains to what we're doing. The Van't Hoff, I'm showing it in these formulas like it is, like you see here. It's also in the osmotic, not osmotic, it's also in the vapor pressure formula, but the Van't Hoff on that one's actually going to show up in the mole fraction because it's all about the, I'm going to jump back to that problem. It's all about the number of solvent particles in solution, so the Van't Hoff would have had to come into play right here. In other words, it's not as straightforward. You can't just take your answer and double it. You have to double the moles here, the moles of the solute, if there's a Van't Hoff. Okay. Some other stuff I was going to say, like as we were doing osmotic pressure, there's a section in your book that talks about like intravenous fluids, and you can kind of see that with physiological saline. Y'all, when you're given an IV, it's important that the IV solution is isotonic with the blood, okay? Same concentration solution. You've heard the terms hypertonic and hypotonic. Hyper means more than, right? So a hypertonic solution means it's more concentrated. And what's going to happen is if it's hypertonic and the solution's more concentrated, then your red blood cells are going to try to dilute the solution because, as we said, it's moving from dilute to higher concentration. So the blood cells would start to get rid of their solvent and they would shrivel up. Okay, versus a hypotonic solution is less concentrated, and the blood cells are going to start to absorb the solution, and they would swell. I mean, this would be deadly. If you had an IV solution that wasn't isotonic with your blood, then you're going to have way more problems than whatever started the need for an IV. But I mean, that's just some practical application of osmotic pressure, and there's a little bit more in your book with diagrams about that if you're interested. Because sometimes, for me, the practical application helps me to understand better what's going on, and it just makes it easier to learn. Okay? And so I believe that covers sections 13.5 and 13.6 in your book. And there's more practice problems in there if you're interested in working them.